Hello everyone, myself Dr. Vipin Kumar. I am presenting this course Electrical for GATE and IES in 10 minutes. This is all about me. I have studied from BIT Misra and IIT Kharagpur. I have qualified GATE and IES. This is the overall course objective. The goal is to guide you in your self-study for GATE and IES, make you familiar with the concepts and numericals asked in these exams, and help you in solving your doubts. This is the first lecture of the series. In this lecture we will study about electrical circuits. So this is the syllabus for electrical circuits for IES 2020. The full syllabus is given at UBSC website, which can be accessed from the link given in the description of this video. This is the syllabus for GATE 2021. It is available at the GATE website. The link is given at description of this video. First, we will study about important concepts and formulae which are asked in previous GATE exams. After that, we will solve some numericals. So guys, we move on to the concepts and formulae. First concept is about electrical current. As you all may be knowing, it is the rate of change of charge per unit time. I is equal to dq by dt. Now Ohm's law states that the current flowing through a conductor is directly proportional to the voltage applied across its end. It is given by V is equal to IR. Now this resistance R, this is given by R is equal to rho L by A, where rho is the resistivity of the material. Resistance at any temperature T is given by R0 into 1 plus alpha delta T. These are simple concepts. You may be knowing them from class 12th. It is just to revise them. Next concept is electrical power. Electrical power is the rate at which electrical energy is transferred by an electrical circuit. Now this power is given by the product of voltage and current, and on simplification it is equal to I square R and V square by R. So a brief about important concepts and formulae related to a current carrying conductor is given in this slide. The magnetic flux produced by a current carrying conductor, which is phi, is directly proportional to the current flowing through it. This is N phi is equal to Li, where L is the inductance of the circuit. The inductance is further given by L is equal to mu 0 mu r n square A by L. Now the EMF induced inside a current carrying conductor is given by V is equal to minus N d phi by dt. This is as per Faraday's laws. On simplification it is equal to L di by dt. The magnetomotive force produced inside the conductor is given by the product of reluctance and flux. The formula is given in next slide. Now mutual inductance between two current carrying conductors is given by M is equal to K N1 N2 by S, which is equal to K under root of L1 L2, where K is the coefficient of coupling, S is the reluctance. Now capacitance is given by Q is equal to Vc, and C is equal to epsilon naught A by D. So this slide contains some important formulas. Please note the formulae for series and parallel connection of resistance, inductance and capacitance. These are important. Now dot convention. What is dot convention? Dot convention is a technique which gives the details about voltage polarity at the dotted terminal. This information is useful while writing KVL equations. If current enters at the dotted terminal of one coil, then it induces a voltage at another coil which is having positive polarity at the dotted terminal, and vice versa. So we will understand this dot convention through some examples in the next slide. For example, in figure A, current I1 enters the dotted terminal. So the voltage induced at the dotted terminal in coil 2 V2, this is equal to positive M di1 by dt. Similarly, in figure B, the current I1 enters the dotted terminal of coil 1, so it induces a positive voltage at the dotted terminal of coil 2. So the dotted terminal is downside. If we measure the voltage from upside to downside V2, this will be minus of M di1 by dt, because voltage is positive at the downside. Similarly, in figure 3, the current I1 leaves the dotted terminal, so the voltage will be negative at the dotted terminal in coil 2. So V2 is equal to minus M di 1 by dt. If you have any doubt in this, please comment on the please comment below and I will answer it. Next important concept is star delta connection. In the figure, the circuit ABC, the outer circuit consisting of resistances ZA, ZB, ZC is the delta connection, and the inner circuit Z consisting of Z1, Z2, Z3 is the star connection. So so the delta connection and star connection, the interrelationship between them is given by the formulas. Z1 is equal to ZA ZC divided by ZA plus ZB plus ZC, and ZA is equal to Z1 plus Z2 plus Z1 Z2 by Z3. So you can simply remember them. So the Z1 is equal to ZA ZC, the two resistances around it, divided by the sum of all the three resistances. Similarly, for delta connection, the resistance ZA is equal to the resistances around it, summation of those Z1 plus Z2 plus multiplication of those Z1 Z2 divided by the resistance which is not around it, that is Z3. Next important concept is Kritchop's current law and voltage law. KCL states that the algebraic sum of currents entering a node is 0. KVL states that the algebraic sum of voltages around a closed path is 0. We'll see these equations in numericals. So these theorems are important for solving node and mesh equations. Superposition theorem is another important theorem. It states that if we remove if a circuit contains more than one source of energy, that is voltage or current, then the combined effect of all the sources equal to the addition of individual effect of those sources. We'll see them in the numericals. We will see some important theorems. So nothing complex about these theorems, they are just the simplification of circuits. So Thevenin theorem, it states that a circuit can be reduced to simply a voltage source in parallel with a resistance. So basically we simplify the circuit. Similarly, Norton theorem, it states that the circuit can be reduced by a current source in parallel with a resistance. The maximum power transfer theorem, it is a important theorem. Some direct objectives come from them. So the theorem states that the maximum amount of power will be dissipated in the load resistance if it is equal in value to the Thevenin or Norton source resistance of the network supplying the power, and for complex impedance it should be conjugate of this impedance. Simply it states that the internal resistance should be equal to the load resistance, that is load resistance should be equal to the resistance of the circuit, then power transfer will be maximum. And if the load is complex, like it is impedance, then it should be conjugate of the impedance of the circuit. Now some questions involve dependent sources, so nothing to worry about dependent sources. Sources are dependent on some current value or some voltage value of some branch of the circuit. So we will simply write the equations and solve it, so nothing to worry about them. Now we move on to some numericals today. Today we will be covering only one numerical. In the next lecture we will be solving more numericals. So first numerical is, it was asked in GATE 2013. So there are three capacitors, two are in series, C2, C3, and C1 is in parallel to these two. So they have breakdown voltages of 10 volt, 5 volt and 2 volt respectively, and capacitances of 10 microfarad, 5 and 2 respectively. So for this interconnection shown, what is asked, the maximum voltage in volts that can be applied across the combination and the corresponding total charge in microfarad stored in the effective capacitance across the terminals. That is asked, that is the maximum breakdown voltage, maximum safe voltage that can be applied, and the corresponding total charge which is stored in the effective capacitance or effective circuit. So we need to calculate the maximum safe voltage that can be applied to this circuit. Now whatever voltage is being applied to the circuit, that will be directly applied to C1 because it is in parallel, and we know in parallel voltage is same. So we need to calculate the effective voltage, the effective safe voltage that can be applied across the series combination of C2 and C3 voltage, and we have the capacitances. From there we can calculate the charges across these two capacitors. Now in series the charges are same, so we will take the minimum of these two charges to prevent breakdown of the other capacitor. This is how we proceed. We first calculate the effective capacitance between C2 and C3, which is C23 equal to C3 by C2 plus C3, because in parallel we know 1 by C is equal to 1 by C1 plus 1 by C2, and on simplification it comes out to be C is equal to C1 C2 divided by C2 C3. We calculate the maximum charge that can be applied across capacitors C2 and C3 as their breakdown voltages and capacitances are given. So we will use the formula Q is equal to Vc to calculate the maximum current that can charge that can be applied across them. So Q2 comes out to be 25 microcoulomb and Q3 comes out to be 4 microcoulomb. Now the in series combination charge across both of these will be same, so we will take the minimum of these two charges to prevent breakdown of the other capacitor. So the minimum of these two is 4 microcoulomb. So in series maximum charge that can be applied across series combination of C2 and C3 will be 4 microcoulomb. Now the maximum safe voltage across the series combination of C2 and C3 will be given by Q23 by C23. This comes out to be 2.8 voltage. Now the parallel combination of C1 and C23, for that the maximum safe voltage will be the minimum of the two breakdown voltages. So the safe voltage across C1 is 10 volts, so minimum of them is 2.8 volts. So the maximum voltage that can be applied across this circuit is 2.8 volt. Now to calculate the total charge will be the summation of the charge around C1 and charge on C2 C3. So the charge Q1 will be given by V1 C1. V1 will be the effective voltage, that is V23, and C1 is the capacitance that is given. So total charge will be summation of Q1 and Q23, which comes out to be 32 microcoulomb. So we come to the completion of the first lecture. Feel free to ask your doubts by contacting me. Do read, review and recommend the course so that more people can benefit from this lecture.